This is the ISD 555 final presentation for Team 14, presented by Arbus, Eddie, Caitlin, Tyler, Esme, and Yue. Metropolitan transit systems are critical to maintaining a functional infrastructure, and the system has multiple factors which would impact both physical and customer utility models. Our system, the inner city train system, is seeking to minimize the cost associated with downtime, operating cost, and passenger wait times. The inner city train system is composed of three subsystems: mechanical efficiency, demand planning, and maintenance planning. Mechanical efficiency is taking physical design of a train as input to minimize the energy consumption. Demand planning is taking passenger needs as input to minimize the cost of unmet demand. Maintenance planning is taking the maintenance facility setup as an input to minimize the cost of maintenance. These three subsystems are connected to each other with shared variables like energy consumption, numbers of cars per train, and train availability.
This slide outlines the key parameter of our design optimization model, which defines the variable and guides the optimization of our objective function. Some parameters are shared across the subsystem, while others are specific to individual subsystem. These design parameters are based on assumption regarding system physical characteristics and operational condition. For example, to simplify mass calculation, we assume that constant average passenger weight. Use the total mass based on basic car construction. We assume that environmental condition and elevation have no effect on our system. For simplification, we consider flat terrain with the total route distance of 50 kilometers and the train operates at a constant speed of 50 km per hour. In a context of operation and maintenance, we have considered parameters such as train stop time, train availability, maintenance requirement. We also consider factors like total population, available seating, peak hour demand, and associate costs indicating maintenance and wages. In this slide, we present the design variable in our optimization model, which directly impact the objective function of our overall system. These variables are derived from design parameters and are subjected to feasible constraints aimed to achieve best system performance. Variables such as number of cars, average speed are shared between mechanical efficiency and demand planning subsystem. Variable which gives energy consumption cost is shared between mechanical efficiency and maintenance planning. In case of length, width and height, which define the car physical characteristics, are specific to mechanical efficiency. Time between departure and number of stops in a given route are calculated within the scope of demand planning. Variables such as number of maintenance worker and harbor capacity are defined within the maintenance planning.
On this slide, we highlight the intermediate variables of our system. All 30 intermediate variables are comprised of intermediate variables from each of the subsystems, from the mechanical, the demand, and the maintenance subsystems, and they work concurrently with each other for our final system optimization model. On this slide, we're going to highlight the constraints and trade-offs for our system. On the left side of the slide, we have the design and side constraints, which is a combination of all the constraints from each of the subsystems that applies to the overall system. For the trade-offs, for our system level trade-off, when optimizing the overall model, the demand subsystem actually overtakes the maintenance and energy consumption subsystems, as with more demand, it increases the cost of both. So it's in direct conflict with those subsystems. In addition, we have the trade-offs for each of the subsystems listed as they each apply to the overarching system. For the energy consumption subsystem, we limited the total train length due to platform size, as well as the speeds for operational limits and technology limits. In addition, we also limited the capacity of the train due to the standard sizes of infrastructure as well as standard sizes of trains. We also have a trade-off with the demand subsystem by minimizing the amount of stops on a route in order to maximize the stops necessary for our standard set number of trains. For the maintenance subsystem, we limited the amount of hours that an employee can work so that they have adequate rest between shifts, as well as defined a constraint for how long a shift should require to conduct maintenance on a single train to simplify the problem. And we limited the amount of space that the harbor needs to service all of the trains.
These are the objective functions for each subsystem and for the system level optimization. Subsystem 1 minimizes the cost of energy consumed, Subsystem 2 minimizes the cost of unmet demand, and Subsystem 3 minimizes the cost of maintenance. For the system level optimization, the total sum of the costs from each subsystem is minimized. The differences that we see in the system level optimization compared to each subsystem level optimization is the presence of linking variables that couples all of the system's optimizations, and due to the comparably large cost of the unmet demand from subsystem 2, the outputs of subsystem 1 and 3 are heavily affected by subsystem 2. For modeling the system level optimization, we ran the optimization by minimizing the output cost of 3 subsystems. We combined the constraints, variables, and parameters and used the IDF method to decouple the coupled variables by supplementing auxiliary variables, which are the estimations for these coupled variables. Then we set up the additional equality constraint for the auxiliary constraint so that these estimations end up equaling the actual variable value. We assume that the total cost of operation for this train system is the sum of all 3 subsystems and that there are no other costs that need to be considered. We used fmincon function in MATLAB to run the optimization because it can handle both linear and nonlinear constraints from all 3 subsystems, and we use MATLAB for ease of implementation because all our subsystem level optimizations were coded in MATLAB.
We ran the system optimization 5 times, varying the maximum number of cars for each run. This variable is in reality constrained by the size of the platforms and by the power of the train, but this was not in scope for the project since these parameters would fall under different subsystems. When we increased the maximum number of cars that the train could pull, the subsystem responses were what we expected, namely that energy consumption and cost of maintenance increase, while cost of unmet demand decreases. It's worth noting that the subsystem objective contribution for the demand system is 1 to 2 orders of magnitude larger than other costs, meaning that the objective becomes more important at the system level. As a result, the demand-based objectives were prioritized by the algorithm, even at the cost of other subsystems like maintenance, which is why you see the demand F star decrease as the maintenance F star increases. We also saw responses in X star values that were notable, namely that the number of cars is always maximized to meet the most demand. The average velocity increases with more cars because motor RPM rises closer to peak efficiency as it compensates for higher rolling resistance. The time between departure also decreases with more cars because as more demand is met, less cars are needed. The number of workers increased with more cars because additional maintenance needed to be performed. And then finally, the number of harbors available decreased with more cars because there was less trains running in the same time that would be able to meet the demand required. For the post-optimality sensitivity analysis, we first looked at our design constraints. We varied platform length, efficiency, and max motor speed to determine what the impact for the system would be if the constraints were changed. From the analysis, we found that platform length and efficiency ultimately drive no change to the system level objective that is significant, but the max motor speed does when significant perturbations are applied at 30%. We then looked at the parameters and varied the frame mass, ticket cost, and population by plus or minus 10%. We found that the total cost at the system level is highly sensitive to ticket cost and population, with 9.2 to 9.4% changes in total cost with the respective perturbations. The frame mass had a smaller impact though, with only 0.4 to 0.8% change in total cost. As a result, we know that in future analyses, close attention needs to be paid in accurate population and cost projections to ensure that accurate cost models are returned.
When analyzing our results for realism, we turned to a white paper called Operating and Maintenance Costs of Light Rail Transit, written in 1975. This white paper takes a look at a proposed light rail system for Dayton, Ohio, with an initial setup in 1975 and an increased capacity setup in the year 2000. When we look at this, we see some numbers that are similar to ours and some numbers that are different. We see that we have a much higher daily ridership, which we attribute to our demand model, which assumes that everyone in the city rides the train. We do also see that the operating costs per car and per kilometer are within family compared to the Dayton, Ohio proposal, and our exaggerated revenue is due to inflation, which is caused by our increased fare, and the high daily ridership from our demand model. When looking at our subsystem to system comparison, we see that at the system level optimization, we made some trade-offs with our subsystem goals. For example, our maintenance subsystem costs were not minimized as a part of the system level objective because their relative contribution was much less compared to other systems, such as our demand subsystem, which ultimately was the contribution that we prioritized. This indicates that our system will seek to optimize overall, even at the expense of the individual subsystems. For future work, we need to do some changes to our demand curve to make it more realistic, as well as perform additional simulations with that updated curve to better project our unmet demand and its importance to other subsystems. We also need to increase the scope for the subsystems to account for changes in other variables such as engine power and platform operations, and could also model a more complex system that adds things like the length of stop, frequency of stops, and the overall length of the system. Creating a more complex system will allow us to better predict what the outcome of a light rail system on an intercity train will be, and updates to the maintenance subsystem with specific data on train maintenance schedules will allow us to better model how much maintenance will cost for the system. That concludes our presentation. Thank you for watching.